A head-mounted display, both abbreviated HMD, is a display device, worn on the head or as a part of a helmet, that has a small display optic in front of one or each eye. There is also an optical head-mounted display, which is a wearable display that has the capability of reflecting projected images as well as allowing the user to see through it. Overview. A typical HMD has either one or two small displays with lenses and semi-transparent mirrors embedded in a helmet, eyeglasses or visor. The display units are miniaturized and may include quart, LCDs, liquid crystal on silicon, or OLED. Some vendors employ multiple micro-displays to increase total resolution and field of view. Types. HMDs differ in whether they can display just a computer-generated image, show live images from the real world, or a combination of both. Most HMDs display only a computer-generated image, sometimes referred to as a virtual image. Some HMDs allow a CGI to be superimposed on a real-world view. This is sometimes referred to as augmented reality or mixed reality. Combining real-world view with CGI can be done by projecting the CGI through a partially reflective mirror and viewing the real world directly. This method is often called optical see-through. Combining real-world view with CGI can also be done electronically by accepting video from a camera and mixing it electronically with CGI. This method is often called video see-through. Optical HMD. An optical head-mounted display uses an optical mixer which is made of partly silvered mirrors. It has the capability of reflecting artificial images as well as letting real images to cross the lens and let the user to look through it. Various techniques have existed for see-through HMDs. Most of these techniques can be summarized into two main families: curved mirror-based and waveguide-based. The curved mirror technique has been used by Vuzix in their Star 1200 product and by Laster Technologies. Various waveguide techniques have existed for some time. These techniques include diffraction optics, holographic optics, polarized optics, and reflective optics. Applications. Major HMD applications include military, governmental and civilian, commercial, aviation and tactical. Ground ruggedized HMDs are increasingly being integrated into the cockpits of modern helicopters and fighter aircraft. These are usually fully integrated with the pilot's flying helmet and may include protective visors, night vision devices and displays of other symbology. Military, police and firefighters use HMDs to display tactical information such as maps or thermal imaging data while viewing the real scene. Recent applications have included the use of HMD for paratroopers. In 2005, the Light-Eye HMD was introduced for ground combat troops as a rugged, waterproof lightweight display that clips into a standard USPVS-14 military helmet mount. The self-contained color monocular OLED display replaces the NVG tube and connects to a mobile computing device. The LA has see-through capability and can be used as a standard HMD or for augmented reality applications. The design is optimized to provide high-definition data under all lighting conditions, in covered or see-through modes of operation. The LA has a low power consumption, operating on 4 AA batteries for 35 hours or receiving power via standard USB connection. DARPA continues to fund research in augmented reality HMDs as part of the Persistent Close Air Support Program. Vuzix is currently working on a system for PCAS that will use holographic waveguides to produce see-through augmented reality glasses that are only a few millimeters thick. Engineering, science and medicine. Engineers and scientists use HMDs to provide stereoscopic views of CAD schematics. These systems are also used in the maintenance of complex systems, as they can give a technician what is effectively X-ray vision, by combining computer graphics such as system diagrams and imagery with the technician's natural vision. There are also applications in surgery, wherein a combination of radiographic data is combined with the surgeon's natural view of the operation, and anesthesia, where the patient vital signs are within the anesthesiologist's field of view at all times. Research universities often use HMDs to conduct studies related to vision, balance, cognition and neuroscience. As of 2010, the use of predictive visual tracking measurement to identify mild traumatic brain injury was being studied. In visual tracking tests, a HMD unit with eye tracking capability shows an object moving in a regular pattern. People without brain injury are able to track the moving object with smooth pursuit eye movements and correct trajectory. The test requires both attention and working memory, which are difficult functions for people with mild traumatic brain injury. The question being studied is whether results for people with brain injury will show visual tracking gaze errors relative to the moving target. Gaming and video low-cost HMD devices are available for use with 3D games and entertainment applications. One of the first commercially available HMDs was the Forte VFX-1, which was announced at SEI in 1994. The VFX-1 had stereoscopic displays, 3-axis head tracking, and stereo headphones. Another pioneer in this field was Sony, who released the Glastron in 1997, which had as an optional accessory a positional sensor which permitted the user to view the surroundings, with the perspective moving as the head moved, providing a deep sense of immersion. One novel application of this technology was in the game MechWarrior 2, which permitted users of the Sony Glastron or Virtual IOSA glasses to adopt a new visual perspective from inside the cockpit of the craft, using their own eyes as visual and seeing the battlefield through their craft's own cockpit. Sony has released the Personal 3D Viewer, a fully surround sound headset for 3D gaming and movies. Sensix demonstrated at SEI 2012 a gaming and entertainment goggle that included an onboard Android processor as well as hand tracking to facilitate natural interaction. Many brands of video glasses can now be connected to video and DSLR cameras, making them applicable as a new age monitor. As a result of the glass's ability to block out ambient light, filmmakers and photographers are able to see clearer presentations of their live images. The Oculus Rift is an upcoming virtual reality head-mounted display created by Palmer Luckey that the company Oculus VR is developing for virtual reality simulations and video games. Headsets are also planned for use with game consoles, such as the PlayStation 4 with PlayStation VR and Xbox One with HoloLens. Sports AHMD system has been developed for Formula One drivers by Copen Corp. And the BMW Group. According to BMW, the HMD is part of an advanced telemetry system approved for installation by the Formula One Racing Committee, to communicate to the driver wirelessly from the heart of the race pit. The HMD will display critical race data while allowing the driver to continue focusing on the track. Pit crews control the data and messages sent to their drivers through two-way radio. Recon Instruments released on 3 November 2011 two head-mounted displays for ski goggles, Mod and Mod Live, the latter based on an Android operating system. Training and simulation. A key application for HMDs is training and simulation, allowing to virtually place a trainee in a situation that is either too expensive or too dangerous to replicate in real life. Training with HMDs cover a wide range of applications from driving, welding and spray painting, flight and vehicle simulators, dismounted soldier training, medical procedure training and more. Performance parameters. Ability to show stereoscopic imagery. A binocular HMD has the potential to display a different image to each eye. This can be used to show stereoscopic images. It should be borne in mind that so-called optical infinity is generally taken by flight surgeons and display experts as about 9 meters. This is the distance at which, given the average human eye rangefinder baseline, to between 2.5 and 3 inches. The angle of an object at that distance becomes essentially the same from each eye. At smaller ranges, the perspective from each eye is significantly different, and the expense of generating two different visual channels through the computer-generated imagery system becomes worthwhile. Interpupillary distance. This is the distance between the two eyes, measured at the pupils, and is important in designing head-mounted displays. Field of view. Humans have an FOV of around 180 degrees, but most HMDs offer considerably less than this. Typically, a greater field of view results in a greater sense of immersion and better situational awareness. Most people do not have a good feel for what a particular quoted FOV would look like, so often manufacturers will quote an apparent screen size. Most people sit about 60 centimeters away from their monitors and have quite a good feel about screen sizes at that distance. To convert the manufacturer's apparent screen size to a desktop monitor position, just divide the screen size by the distance in feet, then multiply by 2. Consumer-level HMDs typically offer a FOV of about 30 to 40 degrees, whereas professional HMDs offer a field of view of 60 degrees to 150 degrees. Resolution. HMDs usually mention either the total number of pixels or the number of pixels per degree. Listing the total number of pixels is borrowed from how the specifications of computer monitors are presented. However, the pixel density, usually specified in pixels per degree or in arc minutes per pixel, is also used to determine visual acuity. 60 pixels degree is usually referred to as eye-limiting resolution, above which increased resolution is not noticed by people with normal vision. HMDs typically offer 10 to 20 pixels degree, though advances in microdisplays help increase this number. Binocular overlap measures the area that is common to both eyes. Binocular overlap is the basis for the sense of depth and stereo, allowing humans to sense which objects are near and which objects are far. Humans have a binocular overlap of about 100 degrees. The larger the binocular overlap offered by an HMD, the greater the sense of stereo. Overlap is sometimes specified in degrees or as a percentage, indicating how much of the visual field of each eye is common to the other eye. Distant focus. Optical techniques may be used to present the images at a distant focus, which seems to improve the realism of images that in the real world would be at a distance. On-board processing and operating system. Some HMD vendors offer on-board operating systems such as Android, allowing applications to run locally on the HMD and eliminating the need to be tethered to an external device to generate video. These are sometimes referred to as smart goggles. Support a 3D video formats. Depth perception inside an HMD requires different images for the left and right eyes. There are multiple ways to provide these separate images. Use dual video inputs, thereby providing a completely separate video signal to each eye. Time-based multiplexing. Techniques such as frame sequential combine two separate video signals into one signal by alternating the left and right images in successive frames. Side-by-side or top-bottom multiplexing. This method allocated half of the image to the left eye and the other half of the image to the right eye. The advantage of dual video inputs is that it provides the maximum resolution for each image and the maximum frame rate for each eye. The disadvantage of dual video inputs is that it requires separate video outputs and cables from the device generating the content. Time-based multiplexing preserves the full resolution per each image, but reduces the frame rate by half. For example, if the signal is presented at 60 Hz, each eye is receiving just 30 Hz updates. This may become an issue with accurately presenting fast-moving images. Side-by-side and top-bottom multiplexing provide full rate updates to each eye, but reduce the resolution presented to each eye. Many 3D broadcasts, such as ESPN, chose to provide side-by-side 3D, which saves the need to allocate extra transmission bandwidth and is more suitable to fast-paced sports action, relative to time-based multiplexing techniques. Not all HMDs provide depth perception. Some lower-end modules are essentially binocular devices where both eyes are presented with the same image. 3D video players sometimes allow maximum compatibility with HMDs by providing the user with a choice of the 3D format to be used. Peripherals. The most rudimentary HMDs simply project an image or symbology on a wearer's visor or reticle. The image is not slave to the real world. More sophisticated HMDs incorporate a positioning system that tracks the wearer's head position and angle, so that the picture or symbology displayed is congruent with the outside world using see-through imagery. Head tracking, slaving the imagery. Head-mounted displays may also be used with tracking sensors that allow changes of angle and orientation to be recorded. When such data is available in the system computer, it can be used to generate the appropriate computer-generated imagery for the angle of look at the particular time. This allows the user to look around a virtual reality environment simply by moving the head without the need for a separate controller to change the angle of the imagery. In radio-based systems, the wearer may move about within the tracking limits of the system. Eye trackers measure the point of gaze, allowing a computer to sense where the user is looking. This information is useful in a variety of contexts such as user interface navigation. By sensing the user's gaze, a computer can change the information displayed on a screen, bring additional details to attention, etc. Hand tracking. Tracking hand movement from the perspective of the HMD allows natural interaction with content and a convenient gameplay mechanism. HMD manufacturers. Companies that have produced HMDs include Avegant, Atari, Canon, Carl Zeiss Cinemizer OLED, Dacry Smart Helmet, Imagine, Epson, HTC, Immersion Vrelia, Copen Corporation, LASTER Technologies, Liquid Image, Magic Leap, Merge VR, Microsoft, Motorola, MYVU, Nintendo, Novaro, Oculus VR, Olympus. Philips introduced 1998. Recon Instruments, Rockwell Collins Optronics. Note that SEOS, now part of Rockwell Collins, also produced HMDs in the UK. Sega VR, Sensix, Sony. Takara introduced 1996. TD Vision, VPL Research founded by Jaron Lanier, who coined and further popularized the term virtual reality. VPL held most of the early VR patents and created the iPhone, Data Glove, and Audiosphere. Vuzix. Transparent glasses. List of optical head-mounted display manufacturers. Bibliography. Head-mounted displays. Designing for the user. Meltzer and Moffat, McGraw-Hill, 1997. O. Kakmaktian J.P. Rowland. Head-worn displays. A review. IEEE Journal of Display Technology, Volume 2, No. 3, September 2006.